slides. I have quite a bit of slides. I try to get through all of them as fast as we can. I'd appreciate if some of the questions we leave towards the end, because that's just how the timeline is set up. Would like to take a moment of silence for Dr. Katz. He's the one that launched the computer festival that we're participating today, also co-founder of the electrical engineering department here, and a true friend and professor of mine personally. So if we could just have a moment of silence. All right, thank you. If there's actually a track one at 1:30 that specifically geared towards all of the events that Dr. Al was involved with. He did a lot of moon bounce things. And if you're interested in how he was able to leverage his career as a university professor, open up his own company, and as a ham enthusiast, he was bouncing signals off the moon. You can check that out. It's on track one at 1:30. So I encourage you to look at that if that fits in your schedule. With that, this is the agenda. I'm just going to cover personal biography real quick, some of my professional experience, the stuff that I'm doing now that has led to some patented technology. We're going to touch upon some history on power conversion, of which I have demonstration boards up here in sequential time order, just so someone who's not familiar with what switch mode power supplies are, they can at least have a taste for like how the technology has evolved over the years. And we'll talk about some basic theory in switch mode power supplies, topologies, magnetics, and control. And time permitting, we'll go over like some audio amplifier stuff that I'm working in, and some further reading that I currently do, and books that I've used in my own career. So with that, my name is Manny Blanco. I am originally from Cuba, came to the United States around the 80s, lived in Elizabeth most of my life. I got a chance to be related with electrical engineering because my dad was a radar engineering in Cuba. And, because of the political climate with the country, there's not a lot of influx of tools, mechanisms to repair things. So we can't buy anything. You almost have to repair things. So I kind of learned electronics just basically by taking things apart, collecting things people threw away and repurposing. You could argue that it was probably like the early beginnings of the Maker Faire before there was really a Maker Faire due to the political restrictions of that. And throughout my career, I've joined some key organizations. Right now, I'm working towards acquiring a master status in chess, and that requires quite a bit of my time right now. That's a little bit about me. This is my professional career. After I graduated at NJIT, I was working at Avionic Instruments. They're still around in Avenel. What they do there is power converters and static inverters, and basically these are just like the power supplies that energize the cockpit and instrumentation in commercial and military aircraft. I was there for about 3 years. Then I went into working in RF, working specifically designing mimics in RFIDs and RF amplifiers that eventually went into a collaborative project that we were running with Motorola at the time. But this company had a 6-inch gallium arsenide fab. They grew the crystals using the ZZ method. And I was in charge of writing the software for die sorting and testing the dies before they got put in the encapsulation, and worked with a lot of product engineers, a very exciting field. The company was much later sold. Later, I worked for Dialite. They're still around. They do LED indicators for traffic lights and pedestrian stop and decrement counters. At the time that I came on board, all of their indicators were incandescent and they were migrating into LED. This is like 2004, 2005 timeframe where they were converting all of their incandescent bulbs into LEDs. So with my physics background, I was working with like improving the optics and also designing the switch mode power supplies that went into the light engines that they were doing. And one of the last projects I worked on there was the Bellagio air jets that were used for the musical air jets that they display in front of the hotel in Las Vegas. And most currently, I work for Simco Ion. The stuff that we design there are high voltage electrostatic neutralizers. And the area where that's primarily used is anywhere there's conveyed material. I'm just going to go through a few slides on that a little much later. And then on the personal side of things, I repair audio amplifiers at home. I work with several guitar shops, repairing local stuff that people drop off. It's kind of a personal interest of mine. I also build tube amplifiers too. And I kind of like to marry both switch mode power supplies with tube technology. It's funny, as an undergrad, I always looked at these things as two separate entities. But the more I learned about switch mode power supplies and audio amplifiers, in reality, it's all amplifiers, whether it's strictly magnetics or strictly semiconductor driven or tube related. The only difference is the signal. You know, if you're doing like an inverter, you're taking a single frequency 60 hertz inverter and you're switching the DC to get the conversion ratio that you want. There's a gain. So it's, to me, I look at it all as amplifiers, but the field has been interesting the next few years. Again, the company I work for, Simco, they're founded in 1936. They're in Pennsylvania, and we focus mostly on printing and converting and medical area, any material that gets conveyed. So like electrostatics, you wonder, well, how's that a problem? Where take something simple like bag manufacturing or medical catheters. In the case of medical catheters, they'll actually take plastic pellets and they'll shoot it in a pultrusion, and they'll blow the pultrusion up to the diameter of the catheter. The process of doing that causes coulombic friction on the mold itself. So when they separate the mold and they pull out the catheter, you can have particulates on the inner or outer wall of the catheter. So we make specialized electrostatic equipment that will either measure the charge, and then based on the power supplies that I'm involved with designing, will create an antipolar charge so that the particulates are neutralized and they fall off. So it's a non-contact way of cleaning catheters. Other applications where they do that is like Pepsi Cola makes bottles, and medical industry also makes plastic bottles. They also have the same problem. So there's several, in the case of like Pepsi Cola, for example, there's several methods on how to clean the bottles after they make them out of the mold. You can use UV light, or you can use desalinated water, but those require a lot of overhead and operations requirements to maintain those systems. And then yet another clever way to do it, which is non-contact, is using electrostatics by blowing clean compressed air into a mold before and after, and then removing the particulates so that they can put their product in the case of Pepsi, any soda or what have you. Basically, the physics behind that is, opposite charges attract, similar charges repel. And the process in which these power supplies are designed, they'll take either 24 volts DC or 120 volts AC or 220 volts AC or three-phase voltage, depending on what's running in the manufacturing floor. And it'll be power factor corrected so that the current and the voltage looks like a linear resistive load. And then after that, we'll amplify the power through high frequency magnetics to make something as high as like 50,000 volts, 100,000 volts, or a megavolt, depending on the charge level and the manufacturing process that requires that antipolarity to make the object that they're processing. In this case, it could be textile floors or the wood veneering in your vehicle, for example. That's not real wood. That's a process where they'll take a printed material, electrostatically charge it, impregnate it in the plastic, and then mold the plastic around it. So that's areas where you would see a lot of the electrostatic equipment. So what I have in this front table here is kind of like an evolution of how power systems have changed over the years. Obviously, way before Nikola Tesla days, we had lamination transformers that required these EI laminations. I'll pass these around, but you can see, they're very heavy. This is like an audio transformer. This thing weighs about 10 pounds. I won't pass that around, but I'll certainly pass this around. which, when the semiconductor devices were invented in the 1950s, they were very slow. So, much later in the 1970s, they started making them a lot faster. And by making the switches a lot faster, it means that we can make the magnetic material, in this case, ferrite material, switch faster at the magnetic domains to match the switching frequencies of the switching devices. And that gives you kind of an appreciation of the top slide where you have a ferroresonant transformer that's able to create, 5,000 volts at 50 watts to something, some oscillator type of magnetics that has a transformer like as small as a quarter, but like a tenth of the weight. So, that's one of the subliminal things that we get as a efficiency factor. For example, when we design these magnetic devices, nobody wants anything bigger or heavier. They want it much lighter and smaller. Unfortunately, there's no Moore's law for magnetics, so we're kind of stuck with the ferrite devices that we have. So this is like an example of like charging and neutralizing supplies that I've been involved with. These are the specific static point ionizers or neutralizers. This is like a HS nozzle that goes in front of a Coca-Cola bottle to neutralize the area. So we're in the business of also making, contoured neutralizers depending on what the manufacturer needs. And, this is like the internal of a particular manufacturer product. You can see that we put the actual applicator embedded right on top of the power supply. So that bar is just, you feed 24 volts in and then you get something like 12,000 volts out, and it has intelligence in there, of which we have about 6 different patents in this technology, where we're able to detect the charge on the web, on the moving material, and make predictive, from a systems perspective, we can make a prediction of what we perceive the charge to be, neutralize that charge, and then use that information to quarantine the next following charge. Now, to get a feel for how fast these webs are moving, they're moving at like 2,500 feet per second. So they're very, very, very fast. Everybody wants the material processed very fast. So we have patents on the indicator systems, on the packaging systems, and also on the switching systems. Now, this is kind of unique to switch mode power supplies because we're able to, pick a dead time, pick a frequency. We can alter that signal any way we want, whether it's an amplitude, phase, or frequency. So this is a multiple axis control mechanism that we were able to implement because we were using high frequency magnetics. You couldn't do that with a ferro transformer because the laminations are only good for 45 or 60 hertz. And this is like just the output dynamic of the output signal, how we can on the fly dynamically change the signal depending on the sampling time and the information that we have. So we have like a culmination of like 6 patents that we're able to measure the web, measure the material that gets neutralized, sense it, and have these like stripe of sensing time tolerances based on the speed that the material is being conveyed, and then make adaptive changes so that the output of the web is always neutralized. This is just to display the information. So fun with technology, right? That's the theme of our TCF this year. Again, one of my personal hobby things is building tube amplifiers. So if anyone here has electronics as a hobby or not, there's basically 3 methods on how to prototype circuits. This is what we call dead bug method, where we take like a copper clad board and we kind of just solder the components on there to build the circuit and get it functioning. It's a quick and efficient way in some ways to lay out the circuit. The next method would be like a perf wire wrap method, where we take a perforated board that has no copper traces and we do wire wrapping on the bottom, which is kind of a step up from a dead bug method. And then we have prototype boards. If you have not seen one, it's basically a gridded array board with like spring contacts on the bottom that make certain array matrix connections underneath to prototype your circuit. So if you have not explored building circuits this method, I encourage you to do it. It's a fun learning part. In fact, I still do that today to exercise some quick ideas. Sometimes I'll get ideas for components and stuff. There's places around that still sell components. You get them online, but I highly encourage that. So now we're going to get into like, how did the switch mode power supply science and field get started? Well, in switch mode power supplies, we're trying to convey the power and move the power along the system so that we get the appropriate current and voltage. But we don't want to store any of these elements because ideally we'd like to not have any storage at all. But the only components that give us the flexibility to store things are magnetic components, which have the units Henry, made by the inventor Joseph Henry. Magnetics got started basically in ore mining in the 1830s, and that was the exploration of trying to extract iron ore using magnetic methods, these giant magnets. The science hasn't changed since then, but nonetheless, the takeaway from this slide is that magnetic element is nothing more than a copper wire wound on a core, and it stores the energy in a magnetic field. And that is the EMF equation on the bottom there. The units is volt seconds. So in switch mode, and that's kind of important because when we're designing a switch mode power supply, we want to maintain volt second balance as well as charge second balance, which is the next device, which is the capacitor. There's only two elements that can store energy momentarily in electrical systems. Capacitor, invented by Michael Faraday, and basically it's just two plates separated by a dielectric that have the metallurgical geometry of how much charge you want to store, and the units of that is coulombs per second, which is farads. So the early infancy of switch mode power supplies started ironically in the car industry. Back then, GM was like one of the cornerstone manufacturers of cars, and they had cars that functioned without a crank. They didn't have a starter motor. So one of the earlier implementations of a flyback converter was with implementing a starter motor to synchronize, the dead start, top dead center when you crank the car. Why this was important is because without having a starter in the car, people were getting their arm ripped off. So so they needed a way to synchronize like the motion of the crankshaft with the points. This is an earlier system, and there's your magnetic device. GM had a patent on this, and this was basically licensed to other manufacturers, and this actually served us well and still continues to serve us well till this day, as simplistic as that system. The only thing that has been modernized with the proliferation of computers and control systems is you still have the hard magnetics, you still have a battery, but you might have a computer now that can read the location of the piston so that you can fire the high voltage to the spark plug to create the detonation inside the cylinder head. Earlier products that evolved for switch mode power supplies were like in the Apple computer, HP calculator, and that's the Apple IIc that had a true converter. So switch mode power supplies in general are pretty much on every device that we use. We just don't really see them at face value and don't really interact with them, but they're always there, and they're always continue to be there in any product that we use. So in power conversion, this triangle kind of emphasizes power electronics, and why primarily I got involved in this is because I enjoy systems control, electronic devices, and power and energy. So I think power electronics is a field. It's the crossroads of many different fields. So you have to kind of develop an expertise in control systems, switching control, understand signal synthesis and dynamics, understand how semiconductor devices work both in the switch mode and also as a switch. And you also have to know some thermodynamics because you want some of these devices to operate very cold and not overheat your system. So here's like a process of power conversion that's very common. In fact, it's still used today. You can collect sunlight using a solar array. That solar array produces DC voltage. So now you have to have that square box that takes the DC voltage, which is unipolar voltage, to make an AC voltage, which is bipolar, using high frequency switching techniques. Now, once you convert that energy into AC, that's like now you can tie it to the grid. You can use it and resell it to the grid, or in this example, if you want to reconvert it back to DC, you can plug a wall wart, charge your cell phone, or if you're mobile like most people are these days, you could just buy one of these little thumb cigarette lighter, so USB dongles, and connect your phone to that. So you can see like there's constant interaction between the dynamic systems, whether it's collecting the energy from raw resources, whether it's sunlight, hydro, or petro oil, and then converting it into some other electricity that runs your device that you're interested in. So with that, there's classifications of converters. Direct current to alternating current converters are just called inverters. Alternating current to alternating current are called cycle converters. You might wonder, well, why would I want to convert AC to AC? Well, in Europe, for example, a lot of the motors and systems out there run on like 60 hertz. And then some of the systems here domestically run on, in Europe, it's like 50 hertz or 45 hertz in China. Here in the US, it's 60 hertz. So you have to have a way to change the phase angle on the system. So that would be an example of where you would have AC to AC conversion, right? So these are like the components that we're looking at, and some of these components would have to be scaled appropriately for the amount of power that you want to get out of there. So again, we're using inductors, and if you take two inductors and couple them on a core, then you have a transformer. And capacitor is still the two parallel plates, and then you have switches. Now the orientation of the inductor, the transformer, and the capacitor is what tells you, the topology that you're using to generate either a higher voltage, a lower voltage, or an equivalent voltage. So, the secret sauce in this is we'll take a switch, for example, and we'll switch it at a particular duty ratio, and we'll either charge an inductor or a capacitor for a period of time. And what happens once we cut off the selected pulse width modulation period, we can actually integrate that period over the entire switching time and create a filter at the output where we can get rid of all the harmonics and all the switching harmonics and just extrapolate the charge that's left on there for the acquired voltage. Obviously, it's more complicated than this. I'm not showing the actual control system. This is kind of like a fundamental type of power supply that just uses straight rectification for 60 hertz. But the takeaway from this particular slide is that it's a switching mechanism. You're using the diodes in half cycle switching for a full wave rectifier in both directions. And it just shows you that there's some sort of switching technique, as fundamental as it is with a single diode. And the switching technique is called full wave rectification, so that we could fully utilize the voltage and current of the transformer throughout the entire 60 hertz cycle, which is shown on the bottom there as the sine wave. And on the top, as you charge the capacitor, obviously, if you pick a big enough capacitor, you can make that line completely flat and get rid of ripple. As I mentioned before, switch mode power supplies are categorized based on the orientation of the switches, the inductors, and the diode. So in the top case, we're switching, we're bucking. Bucking means we're taking a voltage that's higher and we're going to create a lower voltage than the input voltage. We call that bucking. And then boosting is the opposite. We'll take an input voltage and we'll make it much higher than the input. So the interesting thing is we can take the boost topology, for example, reorient the component, specifically the inductor, as such, and then there's no reason why we couldn't make this a two-winding coupled inductor, insert a transformer, cut the traces, create isolation, and basically that's what you have, a coupled winding, and now we call that a flyback converter. So, we could take these non-isolated topologies, and wherever there's a coil, we can insert two magnetically coupled devices to make it an isolation. And there's quite a bit of topologies. I'll get into in a second, but the takeaway from this slide, using high frequency magnetics with Faraday's law, we have ferrite material that we can switch on very, very, very fast. And, based on the saturation densities, which is shown on this BH loop, which is the property of the magnetics, we can select an operational point where we're not saturating the core in either extrema and still be able to get the amount of power. Now, the width of the BH loop just tells you how much power loss there is in the magnetic device. Not explicitly shown on here, but it gives you the trajectory in which how the domains are magnetized, lined up, and then unmagnetized in random order. Let's see here. This is basically a data sheet for the ETD34 3C90 material. You can see that, you know, the tray that I passed around with the switch mode high frequency magnetic devices, some of those are different volume, and what tells you what volume of core to use is predicated on how much power you need, and the amount of power is shown on this BH loop once you integrate over the area of the switching frequency. Now, there is a lot of room for interpretation of the efficiency of the magnetics, and this is kind of like the science behind the magnetics. So believe it or not, how you lay and wind the wire, whether you're using a straight lay, a progressive lay, or a sectional lay, that determines how efficient the magnetic mechanism is, all wound with the same amount of turns ratio. But the only difference is how you geometrically are winding the transformer. So there is a bit of an art form that has to be looked at in here. And somehow after years of experience, you can use intuition to, okay, I want to reduce this amount of loss, copper loss or heating, because that's usually how the losses are interpreted in the magnetics. So these are the different topologies. The top ones are non-isolated, and the bottom ones have two inductors coupled magnetically to make a transformer. And fundamentally, these are the basic topologies. There are, you know, sometimes you may wonder, well, how do I know which topology to use? Well, the first criteria is, are you elevating, diminishing, or just isolating the power? And then decide, well, how much power do I really need to figure out how big of a core do you need? And once you figure that out, then you have to search for a core material. You have to visit the data sheet, and you almost have to do a curve fitting to make sure that you're selecting the correct core. Then you have to figure out what kind of winding techniques are we going to use on these magnetic devices, so that once you turn on the power supply, you can get, you know, the efficiency that you want. Now, if this product is going into, for example, a charger or some domestic device or some scientific device, you also have to take into account compliance testing. You know, when they do EMC testing for approvals, because you have to make these devices safe. And depending on where you plan on marketing your device or selling it, United States, Europe, Japan, or Canada, you're going to have to seek, you know, laboratory compliance tests and measurements based on where your product category falls. You know, testing these products can range anywhere between $5,000 and $100,000, depending on the complexity of the product and what product category you're choosing to sell this product in the market. If you're just tinkering with power supplies, you probably don't have to worry about this, but you still need to be worried about it, because if once you start prototyping a product, you don't want to get too far down the hole of prototyping and then find out, oh, I have to add this extra filter in here, and that's going to change my efficiency. So now you have to go back and visit your magnetic material and then rescale everything from the beginning. So it's always good to have a front end analysis of where this product is being sold, what's the power that you need, who's interacting with it, where does the product fall under which category, and all those commercialized areas. So most power supplies fall under the UL 60950 and the EN 6132, which is lab equipment. That's stuff I'm involved with. So some of the tests that they'll do is that they'll take the power supply and put it in an anechoic chamber, and then they'll try to do things to disrupt the power supply and cause it to fail. Some of the tests that they'll do are harmonics, ESD, surge, voltage flicker, voltage dips. And the product is supposed to not pollute primarily the AC source or DC source that you're ingressing your device. And that's done through CISPAR 11 for conducted and radiated noise, making sure that you don't pollute any of the signals. One of the monumental updates in switch mode power supplies was the PWM controller, originally introduced by Signet. Robert Mamano in '76 was able to incorporate in a single IC a PWM, an error amplifier, and compensation techniques all in one IC. And I think this is what catapulted the industry to really miniaturize these devices. This is a very common TL494 set up as a flyback converter. You can see it's got all the fundamental elements in here. A PWM, two comparators. You can set one for voltage or current conversions or both. It's got a flip-flop and it's got a gate driver. Those gate drivers are the ones that are used to drive the magnetics. But for the most part, all switch mode power supplies are arranged in this type of scenario. The only difference between converter chip to converter chip, some of them have the physical switching element embedded in the IC, some don't. Some actually have power factor correcting in them, some don't. It all depends on how you want to scale your system and how your system interacts with what product category you're creating. But for the most part, those are the fundamental building blocks of any switch mode power supply. And again, this is simply done with transistor switches, transformers, and in this case, for a copier, they're using a voltage multiplier up there, which is basically a string of capacitors and diodes, high voltage ones that take something like 1,000 volts and make 50,000 volts for xerography, static capturing an image and then printing it on paper. Most copiers, this is exactly what you would see inside a copier. I think I'm doing all right with time, right? 11:10?
Yeah, it's only 10:54.
All right, so I'll open up with these questions. If anyone has any questions, we'll go back to any of the slides. I just want to just show these slides again in parallel with my personal hobby, which is audio. For example, in the case of the input transformer, most tube amplifiers have two chunky transformers like those there that weigh about 20 pounds or something. And basically they'll take the signal. In the case of the line voltage at 60 hertz, the transformer is $95. Some of them can weigh anywhere between 2.45 pounds to about 8 or 10 pounds. You need two of them because this is a stereo unit. And that's kind of like the proto of what I built there, which is still a working function. But yeah, you can see these chunky transformers. The cost is $90. They weigh almost 9 or 10 pounds. They're 50 watts. They're quite heavy. So what I ended up doing is I created a buck converter to drive all the filaments on the power supply off of 12 volts or directly off the line voltage. So I was able to do that with some of those toroidal elements that I have in there, which is protoed on that amp board. And basically I took the voltage coming in. I chose a buck converter topology because I wanted to be very minimalistic in switching components. I used the TL494 setup as a boost converter. I calculated my dead time based on the gain factor, V out over Vn equals D. And then I picked my on time and off time. The chip lets you contour the frequency. You could use it as an oscillator. These are just some of the calculations that I ran through that. I did some iterative process in choosing the switching frequency from 20 kilohertz to 45 kilohertz. And what that ended up doing is I ended up using a smaller magnetic device because of the increase in frequency, but it also gave me the capability to design a power supply with very low harmonics and low ripple. And, I was able to implement these are some load line measurements I took. I'm getting the same 72, 55 watts, good efficiency, pretty straight linear power there. This is a capture of the oscilloscope and the switching time frames. And, I got a percent error of 5.38 based on calculated versus, actual components. And, you can see that, oh, sorry. You can see that the power supplies, let me see here. You can see that the power supplies, let me say, the actual transformer went from something And you can see as big as that to something as small as that. It's almost like a silver dollar size, and it only weighs about 1/10 of a pound versus 10 pounds. These are some of the books that I've used and continue to visit, good resources. These are solid books. They're pretty much used in any university program. I've classified these books on, books that are, theory-based versus application-based. And some of these are just reference-based. They actually have designs that you can look at and kind of contour them to what you want them to do. Does anybody have any questions at this point, or? Is that a fire alarm?
You had a robot ask a question.
Nah, I don't see anybody online. Hopefully you guys are motivated to build circuits, have fun with circuits. I think switch mode power supplies is a perfect area to explore many aspects of electronics. Obviously inductors, capacitors, transistors, both in amplifier mode and in switch mode. You just got to get in there and start building circuits and familiarizing with that. Are any of you now involved in power electronics or in the field at all? You are? Okay.
And with X-ray power supplies,
Okay.
industrial X-ray to measure metal thickness.
Metal thickness. Okay, so you're probably familiar with this type voltage multiplication and all that, right?
Yeah, the 120 kV X-ray generator using two multipliers like that.
Yeah,
You
yeah.
know,
To activate the X-ray tube.
60,000 volts plus, 60,000 volts minus.
Yeah.
And transformer input in is a variable DC that's chopped.
Okay.
6 kilocycles.
Oh wow, 6 kilohertz.
Yeah.
Why did they use such a low frequency? Is there?
Well, that was because the original old design came out of the 1970s.
Oh, and
They
they
first
wanted.
started doing it with tubes and then with the transistors.
Oh,
You know, but they just kind of kept the old design.
gotcha. So
I've
the
been working with this stuff for 45 years.
no
and it really
kidding.
hasn't changed that much.
No. Well, for accelerator voltages, there's really not that much. What particular topology do you use? The flyback, the two switch forward,
Or
or?
like the flyback, because it's
Yeah.
120 volts, 6 kilohertz coming in, and I think 8,000 volts coming out.
Wow.
And that goes out through the multipliers. I think there's like 10 stages of the
Yeah.
diode capacitor.
Yeah.
But with the losses, you
Yeah.
get to 60,000 volts in 10 stages.
Wow. What's the name of the company, if you don't mind me asking?
Well, it started off as Schlumberger that I worked for.
Okay.
Then Morale Controls bought them out.
L'Oreal. Yeah, they were involved in like military stuff too at one
Yeah,
point.
well,
Right?
they sold out to Lockheed Martin. The line I was on
Okay.
dumped to measure a Baltimore.
Okay.
And I ended up working for a guy who's still out in the Cleveland area. And he's Barb and Steve Kazan, BSK Industries.
Oh.
I've been working out of my garage for him for 35 years. And
Oh.
I fix X-ray generators.
Oh, really?
Yeah.
Wow, I didn't know that. I'd like to get into that stuff. I actually did a portable X-ray for dental. I was consulting with
Yeah,
that.
I fixed a few of those.
And those are kind of interesting, with the handheld gun. They almost look like a handheld gun with a radar shield in front of it. It's a
Dentist I've done work for in Forest City, PA. Was on Scranton.
okay.
And his machines are.
Gendex, maybe Gendex or something.
Yeah, Gendex is one of them.
Oh, is it okay?
Yeah,
The
like-
German company, yeah.
He's got like 3 different brands of X-ray machines, like one in each of the rooms he's got.
Wow.
Every once in a while, something would quit. It's usually on the low end side of the power supply.
Yeah.
I think like 1,000 volts, 1,000 microfarad caps and things.
Yeah, they dry out like
bad,
this.
so
Yeah,
all we had to do is like change the caps and switch.
nice. Yeah, that's a good area to be involved with,
Believe
for
it or-
sure. Yeah, good.
Believe it or not, they're cheap Chinese gun type units like you're talking about.
Are they really?
Yeah, like in the $600 to $800 range. Believe it or not,
Yeah.
maybe even less now.
I
Now, good or bad they are, I don't know.
Yeah.
It's literally intended for dental X-ray use. It's literally a handheld unit like he's talking about. And they're openly available. How good or bad or reliable, couldn't tell you, never used one.
I would be very skeptic about stuff, especially stuff that's related to medical imagery
Sure.
coming from China, because you have to really check the criteria that they're using for the approvals on that.
The shielding you can test. The rest is just, yes, how reliable is the circuitry is the question. You can always test shielding, that's not a big problem.
Yeah,
They throw a paper wet apron over them. So,
Yeah.
like,
yeah.
they're not exposed to much.
Well, that's it. My
That's
concern
a
about a handheld is how much is the operator getting? Because he's right there.
Yeah, well, a lot of them leave
Hopefully, it's
the room.
only used for light use, not a lot of people at one, not one after another.
And most of them are only on a few milliseconds.
Well, of course.
Yeah,
But
good
still,
well.
only in your hand, it is a shield, but it's not as shielded as a guy walking out of the room and pushing a button.
Yeah.
So that's my concern with those. They are a thing.
Yeah, well, most of the ones that I worked on were like anywhere from 30 to 60 kb, and I think like 1 million.
That's
They
a-
weren't on very long,
Yeah,
milliseconds.
Most
Yeah.
people
With
are
a
for
little
60.
tiny, kind of like a fluorescent display that's it's not a chart type of display, it's some kind of a sensor. It's put back to a PC.
Yep.
There's your,
Yeah, they're all solid state sensors. They're not using so many more. It's true.
yeah, they've migrated now to digital image conversion, but the physical tube is still an X-ray tube.
Well,
You
yeah,
gotta drive it.
Obviously, yeah.
Yeah,
signal source.
I don't think
Yeah.
it's a good way to do that without it.
No.
Not practical anyway.
No.
yeah. That's interesting. So they're using X-ray equipment to detect faults in
No.
cracks in material and things like
No,
that?
the stuff I've been primarily working on is metal thickness,
Okay,
like on the steel rolling mill.
understood.
You know, like the metal's going by 60 miles an hour, and they want to have 0.1% accuracy of measurement, repeatability of measurement. So like 1 millisecond is fast enough for a steel mill
Yeah,
to give you a good control signal that you can use to adjust the screw to squeeze the metal or not
Yeah.
squeeze the metal.
good. Any other questions or where the industry is now, where it's going? Obviously, there's, like I said, there's no Moore's law for magnetics. There's been a lot of research being done and trying to embed the magnetics, like the IC people have done with transistors, where there's clearly a Moore's law there that you can, shrink the die size and pack as many transistors in there. There's a lot of these what they call power conditioning companies are looking at embedding the switching and the magnetic device into an IC. Vicor is a company that strikes a name that is one of the ones that are like at the forefront of that sort of thing. They haven't quite done it, but they do have interesting ICs that have embedded single turn magnetics, and some of the power densities that they have. I mean, they got this thing that looks almost like the size of a credit card that can do like 720 watts or a kilowatt. It's very impressive. I would urge you to check that website out. I mean, they're really pushing the envelope, Vicor. But the industry as a whole, I think with the proliferation of gallium nitride devices and silicon carbide with the wide band gap, they're really pushing those devices in charging stations and wireless charging for your electric vehicle, like we have wireless charging for cell phones. So that's like the market that they want to operate in, sort of thing. But we're getting a trickle effect for smaller systems to implement that in. So that's the latest thing that's going on right now in the semiconductor industry, which is GaN devices, gallium nitride, and SiC devices, silicon carbide devices. And the magnetics hasn't changed really, other than looking for more efficient material. We can't really shrink the magnetics that
They
much.
shrunk them by raising the frequency, but you can only practical to go so far.
Yeah, you can only go so far. So, that's really what's going on in the industry. I think there are just so many topologies. I mean, the ones I just covered on here is probably like 12 versions of topologies. There's actually truly probably like 35 or 40 topologies. Those just happen to be the most popular ones that have been implemented in industry. But I think there's two areas that really need some sort of like, regulation is topology structure and possibly exploration of magnetics. I think, the silicon, we could still continue shrinking that and going in that direction. The semiconductor guys do that very well. But that's like an area where there's not much activity. Any other questions? Sure.
Switching sort of supply versus the generation.
Yeah.
How do they make up the distortion, like for say an audio file or something? Seems like
Really, really, really low. You can actually control the distortion level now to about 1 part per million. Those power supplies are very, very expensive there. I'm a big audiophile myself, and I build amplifiers. I get where they're going with that sort of stuff, but it's like the human ear, first of all, functions logarithmically. You can't tell the difference at that type of distortion level unless you take a piece of instrumentation and hook it up and then look, oh yeah, look at your distortion level, my God. Unless you're running like really sensitive electronics that is being disruptive, or, I mean, now the systems are getting so much clearer in fidelity that you really can't, your ear can't discern it.
they get more dirty, which is bad feed, like that's potentially bad for the body. I mean, that's sort of the thing that's
Bad for the what? For
biology. It's bad, like,
Oh.
if you sit by one of these transformers, these switching transformers,
Yeah.
you get stressed out, and you just
Yeah. Well, I think that also falls back into if you're talking about a consumable product that consumers are going to buy and use, that falls back into the testing. The hard, it used to be, from a control systems perspective, people say, okay, we need phase margin of 45 degrees. Okay, that used to be like the sweet spot for the majority of power supplies. But I've seen phase margins that are way above 45 degrees and also way below. So there's really no like set rule like in linear brute force power supplies where you could say, this is the gain factor I want, this is the noise level I want. The noise level is the noise level. You just have to figure out how to quarantine that. But in switch mode power supply, it's kind of different because I've seen like a lot of the dynamic noise issues been treated like, okay, we really need this amount of power, this amount of current, and how much ripple do we have? 10% ripple good? 30% ripple good? What determines the ripple? What's a good ripple number for you? It all falls down to what is the system driving? Is it driving an EKG piece of medical equipment? Then yes, you don't want to have 10 millivolts of harmonic noise on top of the DC that you're getting out. You want to have maybe 1 millivolt or less. Is the thing being used in aerospace? They're even more stringent. You can't even use, when you're designing for aerospace, let me see if I get that. Power supplies that are used for like celestial travel, NASA uses them. Well, this is the pinch saturation point. When you're designing those power supplies for them, you got to operate down here. You have to have like a level headroom of like 50% headroom. So you're losing almost a quarter of the BH loop just because they don't want any harmonic noise being fed into their systems in a satellite or in some sort of orbiter. And those are just like limitations that they put on that. So then that gets you into, okay, I can't use the 3C90 material. Maybe I got to use 3R1 material. But then you find out that the 3R1 material is very rectangular and square, and now you've grown the core by a certain percentage of the volume. In the case of being used for NASA applications, they're going to say, well, we can only give you X percentage of the payload for the power supply. So now you're looking at interleaving power supplies that you might be able to use this 3C90 material, but now you're paralleling and making the system redundant because of failure mechanisms and quality issues and things like that. So that's the type of thing that you're going constantly back and forth with magnetics, looking at things, many different parameters. Have any of you ever designed a transformer or anything like that? It's a really exciting science, and it's almost like an art too. It gives you a level of creativity that you don't really see at face value. I've seen identical structures wound from different, when I design power supplies, for example, I'll go out and I'll outsource like 3 or 4 different vendors, and I'll tell them, this is my criteria, because we don't have winding machines where I'm at. And I'll tell them, wind it straight, progressive, and I'll check for all sorts of things on a frequency response analyzer. And I'll be able to see like, well, how flat is this? How off is this? And I can tell right away, oh, this was designed correctly. And then when you start loading the power supply, you start looking at it, you're like, well, it's the same core, the same copper, the same arrangement, but the wire lay is different. You know what I mean? Something as simple as the isolation tape, 1 layer versus 2 layers, separate bobbins, all sorts of different things. So, you just have to experiment with the specific topology that you want to use, and then go beyond that and experiment with the physical topography and how the wires are wound on the core. So there's a lot of room for imagination and creation in magnetic design. So any other questions? Good. All right. Well, thank you for being such a good audience. And again, if you want to learn more about Al Katz, there's a track 1 at 1:30 that talks about in detail some of the stuff that he was involved in. And with that, thank you very much and enjoy the